Good morning, students. Today we will discuss about wave nature of matter. Wave nature of matter, or you can call it as wave nature of matter particles. Matter particles are nothing but, for example, you can take electron, it is a matter particle, or proton, it is a matter particle, or neutron, it is a matter particle, or the small particles are called as the particles of the matters are called as a matter particles. Let us consider here, according to Einstein, you studied that one in the last class. According to Einstein, what he is telling, the radiation is also behave like a particle. For example, this is a photoelectric experiment. According to photoelectric experiment, whenever the light is incident on the metal surface, suddenly the electrons are ejecting from the surface of the metal. Here electron is a particle. In order to emit this particle by using a radiation, how come it is possible? In order to emit this particle, the light became the reason, in the sense this radiation is also having some particles. Until and unless it is having the particles, it is impossible to emit the particle from the metal. Here electron is a particle. Here we are emitting the particle from the metal surface by using the radiation. Why? Because the radiation is also consists of smallest particles. Those particles are called as photons. The light, in the sense according to Einstein, the light is also made up of smallest particles. Those particles are called as photons. Because of these particles, we are emitting the particle from the metal surface. That's why the light is also behave like the particle in nature. This is the explanation given by Einstein. The photon or the radiation is also behave like the wave nature, and it is also behave like the particle nature. And this is the explanation given by Albert Einstein. Here in this theory or in this concept, one of the scientists called as Broglie. His name is Broglie. He assumed that the light or the radiation is behave like a particle as well as a wave. The light, however, the light behave like the particle nature as well as a wave nature. According to Einstein, the Broglie assumed that the particle is also behave like a wave nature. Means the particle is also behave like a light, wave in the sense radiation. However, the light is behave like a particle. However, the light in the sense light are also called as a wave. Wave or light or radiation is same. However, the light is behave like a particle. Similarly, particle is also behave like a wave. In this concept, the wave in the sense we need to study about the wave nature of matter particles. For example, the matter particles in the sense it may be an electron, it may be a proton, it may be a neutron, or for example, the cap of this marker, its very smallest one or a small stone, these are considered as a particles in the nature. What he is telling, let us consider here one small particle is there. This is a point and this one is a B point. Here one small particle is there. It is having a somewhat mass or very negligible mass, whatever it is. This is A point, this is B point. I am throwing this particle from here to here. Whenever this particle is moving from this point to this point, we are seeing only straight line. That is depending upon its velocity. If this particle is moving with very high speed, then we are seeing its path as a straight line. We are not seeing these variations are the path in the form of waves. Whenever this particle is moving from A point to B point with very high speed or very high kinetic energy, we are seeing its path as a straight line. Just you can imagine, whenever this particle is moving from A point to B point with very low velocity, then this particle is also associated or moving in the form of these smallest variations. Sometimes these variations we are not seeing because our eye cannot sense these variations. Instead of these variations, we are seeing only as a straight line. But actually this particle is moving with the smallest variations. What are these variations? Those variations are nothing but the smallest wavelengths. If you zoom these variations and observe very clearly, then you are getting the pattern of that path as like this. That's why whenever this particle is moving from one point to another point, then it is associated with some kind of waves. It is also moving in the form of waves. Those waves are called as matter waves. What are the matter waves? The matter waves are nothing but these are the waves associated, or these are the waves associated with moving material particle. For example, whenever this particle is moving from this point to this point, this is moving with the smallest variations. If you observe very clearly what are these observations, then these observations are nothing but these are the smallest waves. It is this path having the smallest wavelengths. Means this particle is also having some kind of waves whenever it is moving from one point to another point. Then these waves are called as matter waves, or also called as de Broglie waves. Why we are calling it as a de Broglie wave? That is just the name after that scientist. His name is de Broglie. That's why here the de Broglie assumed that, or this concept is also called as de Broglie hypothesis. Hypothesis means that is assumption. Who assumed this one? De Broglie. This also called as de Broglie hypothesis. This also called as de Broglie hypothesis. What is the meaning of hypothesis? Assumption. Hypothesis means assumption. Who assumed this one? De Broglie assumed that whenever the particle is moving from one point to another point, it is also moving like it is also moving in the form of waves. Those waves are called as matter waves. This is also called as de Broglie hypothesis. In 1924, de Broglie assumed that, explained that material particles like proton, neutron, or electron, or a small stone, or whatever it is the particle, the material particles are associated with a certain kind of waves. With certain kind of waves means the particles are moving with certain kind of waves in the form of waves. Certain kind of waves. Those waves are called as matter waves. Those waves are called as matter waves, are also called as de Broglie waves. Why you are calling those are de Broglie waves? That is just the name after that scientist, who is none other than de Broglie. That's why you are calling those waves are called as matter waves, also called as de Broglie waves. The de Broglie waves in the sense, let us consider a material particle. Whenever this particle is moving from one point to another point, it is also moving in the form of waves, and these waves are called as matter waves, are also called as de Broglie waves. And the wavelength of these waves in the sense, the wavelength of de Broglie waves or matter waves can be calculated by using one of the theoretical formula, by using the formula that is that is lambda is equal to h divided by p. Lambda is equal to h divided by p. This is the theoretical formula. By using this theoretical formula, we are going to find out the wavelength of these de Broglie waves or matter waves. For example, let us consider it is the smallest particle. It is moving in the form of waves. These waves are called as matter waves. The wavelength in the sense the length of one wave. What is one wave here? One crust and one drop together we are calling it as one wave. The length of one wave is called as wavelength. The wavelength of one wave means the wavelength of this matter waves can be calculated by using this theoretical formula. Here lambda is wavelength of matter wave, wavelength of matter wave, wavelength of matter wave, and what is h? H is a Planck's constant. Its magnitude you know, Planck's constant, that is h is equal to 6.626 into 10 to the power of minus 34 joule second. And what is p? P is momentum of particle. Here p can also be written as p is equal to m into v, because the momentum can be calculated by using the product of mass and the velocity of that particle. This is the wave nature of matter, and this can also called as de Broglie hypothesis. This is the concept thought by the scientist who is none other than de Broglie. The hypothesis meaning as an assumption. Who assumed this one? Because whenever the particle is moving from one point to another point, it is also moving in the form of waves. Those waves are called as matter waves. Like this thinking is given by who? That is de Broglie. That's why we can call de Broglie hypothesis or de Broglie assumption. In 1924, he assumed that whenever the particle is moving in the space, or whenever it is moving through a matter, that particle is also associated with certain kind of waves. Those waves are called as matter waves, and the wavelength of those matter waves is calculated by using this theoretical formula. Then what is the definition of matter waves? The definition of matter waves, that is definition of matter waves, that is the waves associated with moving material particles, means whenever the particle is moving, it is also moving with a certain kind of waves. Those waves are called as matter waves. The waves associated means the waves related to moving material particle. The waves associated with moving material particles, those waves are called as matter waves, or de Broglie waves, called as de Broglie waves. And the wavelength of these de Broglie waves can be calculated by using which formula? Lambda is equal to h divided by p. And the next concept, the expression for de Broglie wavelength. Expression for a de Broglie wavelength of particle, moving with velocity v. This is the next concept. What is that one? The expression for de Broglie wavelength of the particle moving with a velocity v. Let us consider. I am considering a particle as a photon. Just you can imagine whenever the photon is moving from one point to another point, then what is the formula to find out its wavelength? Let us consider I am considering the particle as a photon. Whenever the photon is moving from one point to another point, it is moving in the form of waves. And how to calculate its wavelength? How to calculate its wavelength? By using the formula as lambda is equal to h divided by t. And in this concept we need to study about the derivation of this formula. That's why the expression for de Broglie wavelength. De Broglie wavelength means consider a particle called as a photon. Whenever it is moving from one point to another point, it is moving in the form of waves. Then the wavelength of that wave can be calculated by using this formula. In this concept, we need to study about the derivation of this formula. Let us consider here. Let us consider if the photon, I consider the particle as a photon here. If the photon behave like a wave nature, behave like a wave nature, its energy can be calculated. Its energy can be given by one of the theoretical formulas, that is E is equal to h into mu. E is energy of radiation, Planck's constant, frequency of radiation. This formula is taken from quantum theory of radiation. Max Planck quantum theory of radiation. Whenever if you take the photon behave like a wave, if the photon behave like a wave nature, its energy can be calculated by using the theoretical formula is E is equal to h mu. This formula is given by Max Planck in his theory called as quantum theory of radiation. And if you assume that if photon behave like particle, its energy is given by or calculated by using another formula, that is E is equal to mc square. Here this is the formula given by Einstein mass energy relation. Einstein mass energy relation. If you consider photon as a wave, its energy calculated by this formula. If you assume the photon as a particle, its energy calculated by using one of the mass energy relation given by Einstein. Let us take this is the equation to energy of photon, mass of photon, speed of photon, energy of wave, Planck's constant, frequency of that radiation. Equate 1 and 2. Then that is h nu is equal to mc square. H as it is, nu can be written as c by lambda. This is equal to m into c square, because you know very well speed of light is equal to frequency into lambda. Speed of light is equal to frequency into wavelength. Then c divided by lambda is equal to frequency. Here in the frequency, I substituted c by lambda. Frequency is equal to c by lambda. I substituted c getting cancelled. H by lambda is equal to m into c. Here what is c? This is speed of light. We can write speed of light as v or c. Therefore, h by lambda is equal to m as it is. Instead of c, I am writing v. V is also speed of light, and c is also speed of light. Instead of c, I introduce the term as a v. Therefore, this one h by lambda is equal to m into v. Here h by mv taken as a denominator, and this is shifted to right side. Then lambda is equal to h by mv. This can be written as h divided by v is equal to lambda. We know very well momentum is equal to mass into velocity. This is the derivation of de Broglie wavelength. The de Broglie wavelength can be calculated by using is a formula derived by the scientist called as de Broglie, and this is Planck's constant, the momentum of that particle, and its wavelength can be calculated by using these two terms. Whatever it is the particle, whenever it is moving from one point to another point, it is moving in the form of waves. Those waves are called as matter waves, and the wavelength of that matter wave is calculated by using this formula. This is also called as de Broglie wavelength. Planck's constant, momentum of that particle, and the wavelength of that matter particle, or the wavelength of that matter waves. And this one is expression for de Broglie wavelength. And next, concept is the expression for de Broglie wavelength of the particle moving with potential difference V naught. Here already I derived here, that is lambda is equal to h by p. That formula is only applying for the particle which are not having charge. For example, that formula is applying only for photon, because photon is not having any charge. But here another formula is there. That formula, that is lambda is equal to h divided by root of 2m ev naught. This is the formula in order to find out the de Broglie wavelength for which particle, the particle which are having the charge. Getting? Here for example, the photon is there, it is not having any charge, its wavelength can be calculated, that is lambda is equal to h by p. But here electron is there, proton is there, these are the particles having charges. Whenever those particles are moving in presence of electrical field. Getting? This is a positive plate and this is a negative plate. This is the electrical field direction. Whenever the particles, for example, whenever the electron is moving in presence of electrical field, then that's why we have taken the potential difference between these two plates. Whenever some particles having the charge, if they are moving in presence of a potential difference or in presence of electrical field, then they are also moving in the form of waves. Those waves are called as matter waves. The wavelength of those matter waves can be calculated by using this formula. What is the difference here? Photon, for photon lambda is equal to h by p because it is a chargeless. But for electron, whenever it is moving with the potential difference between any two points, then its wavelength can be calculated by using this formula. And this is the derivation for the particle which is having a charge and it is moving in presence of potential difference. Let us consider a electron or consider a particle. Now the particle in the sense it is having a charge and moving in presence of potential difference or in presence of electrical field. A particle of mass m and charge E moving with potential difference, that is V naught. Then its kinetic energy of that particle is equal to work done by the electrical field on the electron or on the particle. Let us consider this is the electrical field. Whenever I am taking electron, it is a chargeless, it is having a charge. This electron is moving from positive plate to negative plate because this is the plate, this is the negative potential. In between, it is having a potential, this point and this point. In between the potential difference, the particle is moving. At this side, this electron experiencing the electrostatic force of attraction, and this side it experiences the electrostatic force of repulsion. Whenever this electron is moving in presence of electrical field. It is moving in the form of waves. Those waves are called as de Broglie waves. And in order to find out the wavelength of that de Broglie waves associated with the charged particle, we are going to use this formula. Now we are deriving this formula now. Therefore, let us consider the kinetic energy of particle. The kinetic energy of the particle in the form of stopping potential can be written as stopping potential. You know that kinetic energy is equal to E into V naught. You know very well kinetic energy is equal to 1 by 2 mv square. This magnitude is also equal to K is equal to EV naught. Its magnitude and its magnitude after calculation is exactly same. That's why kinetic energy is equal to, in terms of stopping potential, we are going to write like this. This is potential between those two plates and this is charge of the electron. This is kinetic energy. Let us consider the kinetic energy of a particle with velocity v. With velocity v, that is kinetic energy is equal to 1 by 2 mv square. You know very well this also. This is whenever the particle is moving in presence of potential difference, then its kinetic energy can be calculated by using this formula. Whenever the particle is moving